afternoon session. During my commercial break in the morning, I forgot something to say. Just a small remark. The first 3 emails I will get will receive a free electronic copy of our latest book. So just drop me an email. Yeah, but now we are on our afternoon session. We have actually 2 talks. The first talk will be given by Jakob Rehof. Jakob is currently a professor of computer science at the Technical University of Dortmund, and also he is a director of the new Dharma Institute for Machine Learning and Artificial Intelligence. He was a long director of the Fraunhofer Institute for Information Systems and Software Information Systems, and currently is still the research strategy director of the Fraunhofer. I know Jakob now for a couple of days, and he always is very interested in formal foundation on the one hand, and as you typically say, the aggressive usage of strong theoretical foundations in practice. So I'm very excited to your new talk, and the floor is you for 45 minutes.
Thank you so much, and thank you for inviting me again to come here and give a talk. I'm going to talk about component-oriented synthesis. I've talked about that before at this venue, and so I will just give you a very, very super fast recap. And you don't need to capture a lot of details for that, because I'm going to focus on some new application areas, including neural architecture search, but also simulation that we're trying to target. And I should say that my talk will not dive very deeply into technicalities of machine learning. I will touch, however, on some of the main streams that we're thinking about. Also, I should say the talk is very much ongoing work. So I'm not aiming to sort of present one particular technical result. I rather want to present to you the stream of investigation that we're undertaking. So after a super fast recap of what combinatorial logic synthesis is, I will say something more about its application in what we call search space synthesis or neural architecture search.
Jakob, may I interrupt?
ML. Yeah.
Are you sure the microphone is on?
Yes, it is.
Okay.
It's on. I can hear it. I can feel it in my back. Can you hear me there? Can you hear me in the back? You might want to, maybe you want to get closer to the, okay. And then I will say something that is on my mind very much these days, something I just find quite fascinating, and I'm not done with thinking about this, but I'll throw some of the main ideas at you. Okay, so combinatorial logic synthesis, what is it? At its most condensed form, and this slide is really all you need to understand in order to appreciate at least some of what I'm going to say. Combinatorial logic synthesis is a type-based component-oriented synthesis framework. What does it mean? It means components are typed function symbols, okay? And what does synthesis do? Given a collection of typed function symbols, it gives you all the possible compositions of those functions or function symbols such that a given goal type can be reached, such that the composition has a given goal type. Of course, according to a type system. Now, I'm going to say a little bit about that type system, but we're not going to delve into all the details. I'll just point out a few of its features. So what we're doing is we're synthesizing trees. What is a tree? Tree is an applicative structure in this setting here. That means these dots, these internal dots here, represent function application. So, for example, this tree here is the combinator, the function symbol A applied to a literal X. Okay? Combinatory logic, which is the foundation of this, is automatically higher order, so we can easily talk about applying functions to functions if we want that. That's illustrated here. And of course, composition in the usual sense, not just application, can be obtained by introducing a combinator for functional composition. Okay? And so the whole synthesis is done relative to a repository of such components. And what we do again is I make this remark inspired by Holger's wonderful Lego t-shirt, is really we're playing Lego with function symbols, and the shapes of the Lego symbols are given by types. Okay?
Please stand up.
Yeah, I couldn't have asked for a better t-shirt on Holger today. Okay, so there's an input goal type, there's a given collection of components or function symbols or combinators, and there is a so-called inhabitation algorithm for combinatory logic. That's the workhorse of the synthesis mechanism. That's the algorithm that constructs all possible compositions of functions from the repository having the given goal types. Now, it may be the case that the functions we're talking about might not be sort of written in the end language that we're interested in. And the model of composition is really functional. Okay, but we might want to think about, for example, generating code that's not functional. For example, you might want to generate Java code or something like that. And we can do that, accommodate for that, by thinking of those functions as meta programs, which, when executed, then generate the code of interest. In this case here, where I'm now suggesting applications to something that starts already looking like neural networks, we are really in a truly functional world. One of the interesting things from this viewpoint about neural architectures is that they really are truly functional objects. I have illustrated quite briefly here the use of our type theory that underlies this, which is an extension of what you would know as type systems. It's really based on some pretty high-powered modern type theory, which sort of coincides with modern mathematical logic. And in addition to that, we have an extension using so-called intersection types. That's really a generalization of standard type systems to become multi-dimensional type systems in which one and the same object can have any number of finitely many types. So you can express the idea that something has many types. This is useful, for example, because it allows us to not only talk about the implementation types of some component. For example, f here is a function from real to real, might be implemented in some Python code, for example. But we are able to also add the specification that this component here represents a layer, whereas this component here, which has the same underlying implementation type, is something different because it represents an activation. Okay, so in this way we can inject what I like to call semantic specifications into the types. There's a standard kind of pipeline that we've built that's also been closed into a loop where we start to get in contact with learning applications in machine learning. One example of that I have taken from some fairly recent work where we were working on generating sampling-based motion plans to control robots. And so if you look at this cycle here, you get from synthesis something which then becomes translatable into executable programs, in this case these motion plans. And by adding a learning component, in this case a tool called Hypermapper 2.0, we are able to walk around in a configuration space. So these sample-based motion plans have various configuration parameters, and now we are trying to use synthesis as a basic motor for doing optimization, essentially. Okay, so think of the synthesis engine as like a gun that is able to spew out, lots of different possible solutions to a problem. But then you start looking at configuring various, in this case, numerical parameters around those solutions, and you feed that back into the component repository. And inside here, there is some Bayesian optimization going on and some random forest going on that systematically try to walk around in a parameter space and then close this loop to keep generating new solutions and to see which solutions are better. And what it does here is it automatically produces a Pareto front for this particular setup. As I said, I have some slides coming up now, which I should not deter you. I just wanted to point out that there is some I think, nice formal foundation to this work in terms of dependent types with predicates. And the nice thing about this system is that it's possible to single out a kind of a fragment of this formal system that is decidable. In general, these problems become undecidable, but we have a characterization of a decidable fragment, which is interesting also from a practical perspective. And since the problem can generate infinitely many solutions, it's possible to have setups where the synthesis process will produce infinitely many solutions. We need to think about how to represent those, and for this fragment it's very satisfying, I think, that it turns out that solution set can be represented as a Horn theory. Here's the language of types. We got these intersection types here, we got function types, we got type constructors, but then we add a layer of parameterized types. These forms here are universally quantified types in the sense of dependent type systems. If you don't know what that means, it doesn't matter. Those quantifiers then can be combined with predicates. In this case here, you've got literal symbols that are quantified alpha, and here you've got term variables that are quantified. The literal symbols can be used to express the presence of various kinds of, for example, numerical parameters, and that's going to become important for the optimization problems I'll talk about. So, for example, here you have alpha and beta ranging over pairs of natural numbers, and we can use that to specify some mechanism to move around in a maze, for example. And we can have predicates on those literals. We can also have predicates on terms. That is, we can, for example, express the idea that we want the trees that we generate to be such that, for example, two subtrees designated by the variables must be the same. Okay? So we can express things like that. So that's a very expressive system. Here's the little language of combinatory expressions. That's the language of trees that I already showed you. This is the type system relative to which everything takes place in the synthesis part, because that defines what it means to be a well-typed composition. I'm just showing you that to show you that it's there, and also that it's not, horrendously big. I think of it as a fairly elegant system, but I'll not get into the details. I will say that synthesis is now well defined once you have this system, because synthesis really means solving the problem given a repository that's split up into two sets, gamma and delta here, doesn't matter, and the goal type tau. Can you find all possible combinatory terms, that is trees, such that they have each of them the goal type tau in this typing context. Typing context play a role as kind of sets of hypotheses relative to which the typing takes place. Okay. I refer now to the set of all possible trees. That's called inhabitants in type theory. An expression having a certain type is called an inhabitant in the type, and they sometimes will slip into that lingo. That's why I mentioned it here. I will call that H of gamma delta tau. Okay, so that's what synthesis is. Now I will say a little bit about how we yes.
And it is important that you get the entire set.
Yes, it is.
Okay.
We like to get the entire set, but I will say that it's important that we're able to get the entire set. For some applications, we are not going to be able to exploit the entire set because it's too big. It might be infinite. So what we then do is we either filter further on it, or we start enumerating, or we even start sampling from the set. Okay, so that is the stage before we can then do all of this stuff. In this context also, one of the reasons I really love the fact that we have this fragment with a horn clearly representation of the solution set is that it gives us a very natural way to think about hooking up further tools like constraint solvers, for example, to zoom in the solution sets.
And then also do uniform sampling or something like that?
Yes, we could also, I mean, we can, the solution set now is a programmatically represented object and not in, you know, not in some home-cooked format, but as a horn theory, so that you can throw logic programming technology in. So AutoML, and now it's a little bit about what we are sort of working towards doing by bringing this synthesis technology together with the area of AutoML. As the name suggests, AutoML is a field of research in machine learning where people are concerned with trying to, as automatically as possible, optimize machine learning architectures. Okay, so that's a real practical problem now that machine learning is penetrating into all kinds of other disciplines. So you have a lot of non-experts working those disciplines, for example, physicists or biologists or whatever, who want to use this technology, and for a given task or a given scenario or class of scenarios, you'd like to be able to select the machine learning architectures that are well suited for the task. Moreover, you can also use automatic search for specific architectures as a more sort of foundational tool, research tool. If you imagine, for example, being interested in trying to understand causality within these models, these machine learning models, or you might be interested in trying to understand, for example, modularity of these models. So you automatically try to compose various elements of the machine learning architecture in order to try to understand what its impact, what the impact of certain changes in the architecture would be. There are subclasses of AutoML, basically neural architecture search, which I kind of put on the title slide here, but I could also have put HBO on it. Neural architecture search is really about searching for architectures by exchanging different structural components. For example, the topology of a network, or exchanging one kind of activation function, for example, some kind of sigmoid function, with a different kind of activation function, for example, a ReLU function. So that structural variation in the solution set we're talking about here. Whereas HBO, hyperparameter optimization, is more about optimizing numerical parameters. That could be like the learning rate of a neural network, or it could be the number of neurons, for example. Those would be given by numerical parameters. And so people try to throw optimization techniques at these problems in order to find the best configurations of the machine learning system for a presented given scenario. Everything I'm talking about today is also useful for something that we've been pursuing quite a bit in the past, namely the automatic generation of simulation models. Okay, so we're now turning the synthesis tool into a tool for synthesizing machine learning architectures. That's the neural architecture search aspect here. And we're basing that on a theoretical foundation, which I think is quite interesting. Coming out, at the end of the day, coming out of categories here. And that began, that line of work, with a paper by Fong, Spivak, and others that appeared at LIX. That's the leading conference on mathematical logic in the world today, 2019, which was called backprop as functor. Functor is a concept from category theory. And what they were trying to understand is what really is a learning mechanism, and in particular they were interested in the class of learning mechanisms based on backpropagation. And that set a line of work in motion leading to a contribution that we are using, and also, I mean, we're adapting that to our setting to have like a very general but completely formalizable theory of what a learning system is. Again, I don't want to get into the details here, but of course you can see the structure has two movements in the arrows here. There's a forward movement and then there's a backward movement. And the forward movement represents here the forward propagation of parameters and weights during learning. Okay, so that's a forward move from the input to the output of the neural net. And the backwards direction is the back propagation process that does the optimization of the weight values. You can see here then different components named here, and those would typically in some form or other correspond to combinators in the repository that now get composed into this picture. Here, for example, atom W is a specific kind of non-gradient based optimization algorithm that is often used but not always used, but often used in these scenarios. And this diagram here represents one very tiny solution to a kind of a little toy problem that we put together for the purpose of presenting the ideas. Okay, so here you see other things like bias, ReLU. The number of layers might be different in a different solution on this slide. I'm suggesting a number of different solutions here. You can't, unfortunately, really see that very well, but here, for example, you've got the ReLU activation function element here, whereas here you have a sigmoid function. So that's an example of what I mean by structural variation in the solution space. Why is this of any interest in practice? Well, this model, this foundation in this categorical model of backpropagation systems provides a lot of structure in terms of how to design the space of functions and their types that go into repositories. So this is a great help. This is that here you're profiting from the fact that these machine learning classes of systems are mathematically very well defined. Okay? So there really is a mathematical model behind it. And what this theory does is it allows you, in some sense, to translate interesting structural features of these mathematical models into a language of logic that is accessible to our synthesis framework. So you're not left alone if you're trying to come up with a way of constructing combinators and types for a given set of scenarios. There's a theory behind it which can be understood, and then you also understand how to structure your repositories. For example, here's a repository again. We're not supposed apparently to read the details of it, but this is a repository. There's a combinator called layer, bias, ReLU, sigmoid, and so on. You saw it in some of the diagrams before. These are then the types. You see, I hope, that the specifications are not hopelessly complicated. What comes out of the synthesis now is a horned program, a logic program. For this particular case, here's the actual logic program that gets automatically generated. And this program will now recognize all possible solutions and only possible solutions. It will define the set of possible solutions to a query based on this repository of functions. And then you get this space of solutions. Now, those solutions with these nice diagrams, of course, then get compiled into something that can actually run and be executed as machine learning systems. In this case, we're working on top of a well-known machine learning implementation framework called PyTorch, which automatically takes care of the backpropagation and a lot of other of the optimization functionality that you need when you do machine learning. And as I already suggested a little bit, one of the things that interests us is to use this automated variability to try to investigate in an automatic way different kinds of properties that one might be interested in for machine learning systems. For example, understanding causality, like for example trying to understand if I use this ReLU activation function instead of this sigmoid function here, what effect, if any, does it have on some other property of the system? Maybe the ability to recognize some given object, or it might also be, does it have any effect on some other part internal to the system? Okay. So there's a number of advantages to this approach, which I put here on the slide. I don't want to read it off the slide. I will say this, that again, I think it's interesting that the whole thing is really placed squarely within standard modern mathematical logic, and also using categorical structures that have turned out to be very interesting, in particular in the context of modern functional programming. Now, I will move on to the last topic of my talk, and I have about 15 minutes, some 15 minutes. So now I'm interested in, and this is part of sort of the ongoing work that I advertised before, and again, it's not finished. I'm interested in developing a formal theory of experiment here. I already suggested in my previous sentences what I mean by an experiment. That is, I make a change here, and I want to see what does that mean for some properties in the rest of the system. And I want to see if I can try to do that in a systematic way. And I'm particularly interested, of course, as a kind of a formalist also, in asking questions like, could we be helped by any algebraic structures, for example, coming out of the categorical foundations in this endeavor? Okay, so now I made the transition to the last part of the talk, where I will talk about moving towards a theory of experiments for this concept. So, what does that mean? It means that I look at sets of trees. That's my solution set. Okay? So I look at my solution set as defining the set of possible experiments that I could possibly do. Okay? The idea is that I only want to work when I make a change to one solution, I want to get another solution. I don't want to get outside the solution space, okay? Because I only want to see trees that are actually solutions to the original high-level specification, if you want. And now I want to fine-tune that solution set, or I want to find structure in the solution set. Make a change here, what does it mean over here? How do I formalize that? And how do I formalize it in such a way that I can talk about the entire set? So for that, I think of trees having sort of this general form with those two triangles here, meaning to suggest some subtree somewhere in a larger tree. Don't get hung up by the graphical fact that they sort of seem to be down at the bottom. It's just a suggestive picture saying there's a tree T, which is an element of my solution set, and that tree has some subtrees. Then there is an evaluation going on up here, which evaluates the solution, the tree, in this case, into some vector of real numbers. So I'm assuming here that we have some measurable types, for example, reals, where we can measure some value of the tree. Okay. Now, in a simulation context, that would mean running the simulation model generated from the tree. And in a machine learning context, it could mean looking at some of the weight values, or it could mean measuring on the output given an input to the model. So from this very general perspective, you can think about parameter variation. That would mean sticking in vectors of numbers which are parameters. They get then substituted for the literals in the generated trees. In the generated combinatorial trees, these numbers would be represented by literal symbols. And that would be relevant, for example, for hyperparameter optimization. But as I said before, I might also want to do structural variation. I might want to actually change the entire subtree at some point with a different subtree. And that would be taking me into the space of neural architecture search. Of course, also I must think about the fact that these variations might be dependent. So if I have multiple places where I want to make variations, there might be dependencies. And I need to be able to talk about that too. So that means here, for example, having two vectors which depend on one another. Now, in order to formalize the idea of what an experiment is, a controlled experiment with variation points and other parts which are held fixed, right? That's the idea of an experiment, a controlled experiment. I'm looking at the concept of contexts, which are trees with holes in them. Now, the holes here are suggested in this way. So a tree can have a hole, and a hole can get filled with different values, thereby creating variance of the tree. In a context would, as I said, typically be something you hold fixed, and then you control different values that go into the hole. So that's suggested by the next few slides here. Can we lift this idea now to sets of trees, and is there any useful structure to be found there? So, the good old idea of a context, I have now written down in grammatical format in the grammar over by combinatorial trees. A hole is typically represented this way, and filling a hole means that you put in a subtree at this point to create a new tree. Okay, this of course now can be generalized to multiple hole contexts by sort of repeating the process of putting in a hole into the tree. Now, at this point, I got very excited when I found out that from a very different and a completely different perspective, people have looked at coming up with models for what contexts are in data structures. Okay? And what does it mean to make a hole in a data structure? And in this viewpoint, you get a very abstract, again, a categorical model of what a data structure is. It's a very extensional view. So in this view, a data structure like, for example, a list structure is given by a set of shapes, and for each shape in that set, there's an associated set of positions, and for each position, there's a mapping to a value of some form. So for example, for lists, you can think of a set of shapes as given by natural numbers. That's just the length of the list. And once I have such a shape, the length of the list, I have a set of positions in the list that would be indexed by the numbers from 1 up to n. And now I can start then filling in values into that list. And in fact, the container is like an extensional type of lists in this case, because it consists now of all possible valuations, of all possible positions in all possible shapes that you can give. So it gives a very extensional view of what a data structure is. And what is on this slide here is simply a recap of what I just said. The extension of a container is written like this. S is a set of shapes, and P of S is the set of positions associated with each such shape. there's a set operator associated with the container which takes a set of values and the extension of the container then becomes the sum of all possible shapes over all possible shapes of all possible functions mapping positions to values in X. Here these sigma sets are taken from something called constructive set theory, which is something that is very compatible to dependent type theory. But I'll just note that that these sigma sets, they are sets, but they're sets of pairs, dependent pairs. So for example, if I have a sigma set of this form, and I have an index set A, and I then have a family of sets BA, then elements of that sigma set would be pairs consisting of an index A and a B from the BA set. So we're talking about families of sets indexed by values from some index sets. Okay, now containers can have higher arity than one. The arity of the container might be used to divide the set of positions up to into different regions, and that's interesting because you can then start composing containers with one another, possibly by filling in new containers at the various positions. So you can have now arguments into containers. Now here's an interesting thing. Given the structure of containers, we can start defining algebraic operators over them. So for example, we can define the sum of two containers that gives you a choice. If I have F is a container and G is a container, then there's a new container which will either take you into one container or it will take you into the other container. There's also a notion of Cartesian product on containers which combine the mappings, the valuations into values into one valuation, set of valuations, taking you essentially from the combined, the union of the sets of positions as the domain of those functions. If you boil this down to the finite case of finite sets of finite functions, you can understand all of this as really Cartesian products. Okay, so now there's a notion of composition of containers, and so this essentially means that you have a mapping that takes you from the position set in one container, and you map into the position into the shape set of the composed container. So this really means filling in the container G into H at the parameters given by the arity of H. Note here that we're assuming here that we're using the full function space. Again, a container is like a type. It's a free construction. All possible values are considered. It's like a type in this sense. It's not a particular list. It's the type of all possible lists. So now I need to speed up because I absolutely need to tell you one last thing before I leave the talk. Now, the idea that I'm working on is to do something which is a little not normal in this line of work, namely to consider something that's in between a container and the value in a container, namely a set of values in a container, and look at how much structure such arbitrary sets of values might inherit from the container structure. And so I don't have time to really fill in all the details here, but the basic idea is that in a contained set, the valuations from positions to values don't have to span the entire function space. So it could be anything from one particular value, like one particular list in the case of list, or it could be any set of concrete lists. in my case, not lists, but trees. And so with that, we can start talking about semantically evaluating our trees by composing our evaluation functions from positions into trees, and composing those trees, composing with functions that further evaluate those trees. So that's kind of standard. What I want to move to, though, is the idea of now having a hole in such a tree and filling in the hole. So there's a way in this context now of thinking about a hole in a tree, and I've drawn it here. And so the idea is that contexts now are given by positions which are removed from the domain of valuations. This is how you create context in the world of containers. A context arises by removing a position from the domain of positions, because you're no longer mapping this position here to a value. The idea is you're going to fill it in. Okay. And so there's a notion of hole filling, or plugging, as they say in this context. And a contained set of variation points now, together with a family of valuations, is what defines an experiment. So this is now formally defined. We can now formally define what I said before. I wanted to have a formal model of what is an experiment, and that is a nice thing. But there's more, and I wanted to just leave you with that slightly more. So in the last couple of minutes, let me go down a hole and consider something that people have looked at when thinking about filling holes and contexts. Okay, and so Gérard Huet, who was a formidable logician, he came up with a functional curve in 1997. When he was just thinking about how to represent in a functional programming language the act of filling holes into some structures. And so he came up with a data structure called the zipper. What is a zipper? Well, in this case, let's take the case of trees that we're interested in. So a tree is a recursive structure. It's either a leaf or it's a node, and it has two trees. Okay, so that's binary trees. Those are binary trees. The zipper now consists of a type that has kind of an instruction either going to the left in the tree or going to the right in the tree. That's where you want to put the hole. Okay, so you either put the hole to the left in the tree, or you put the hole to the right in the tree. Now a zipper, plugging using such a zipper, is a function that takes this zipper structure and moves through the tree according to the instruction, go left, go right, go left, go right, and at the end, when the zipper is finished, you're plugging in by taking the argument tree and stuffing it into the hole by returning it. Okay, here's an interesting observation. Have you seen this observation before? That's great. It's a nice observation, isn't it? Because the observation is, if you write these types here in a slightly more systematic, again categorically informed way, then the type up here, the type of binary trees becomes a recursive type when the type 1 is a unit type. It's a type that has only one element. That's the leaf constructor here, and the x squared is the Cartesian product of the tree type here. Okay, the interesting observation is, if you look at the type of the zipper, in this case it actually becomes 2 times x. Where does the 2 come from? Well, that's the left and the right. And the single x is the fact that in each case you only have a single tree type associated going left or right. Okay, so that's 2x. Now if we had ternary trees and we imagine the zipper for that, you would, by the same reasoning, come to the result that the type of the original ternary tree is 1 plus x cubed, and the zipper type becomes 3 times x squared. Now, does that look familiar somehow? At this point, I should ask Wolfgang, but he's not available at this point. But does this look familiar? What do you think of when you see this? Anybody?
The derivation.
What?
Derivation.
A derivation. Who said that? You said that. That's a very good You get a plus in my black book now. Yes, that's right. This observation was originally made by Conor McBride back in 2001, I think. And he has a nice story about it, that he was sitting, I think, in some train station in the UK somewhere, and he was thinking about, he had zipper, and he was thinking about the systematic behind the types of the zipper. And he said, well, it's a derivative operation, actually, on the type. But he was not able to explain really systematically what was going on. And so therefore his first attempts to publish this observation failed. His paper was rejected because people said it's not clearly explained what is really going on. You can make this observation already quite systematically. If we have the sum of two data structures, or we have the Cartesian product of two data structures, and we ask what does it mean to put a hole into such a structure, clearly with the sum you could put a hole into the choice of two structures by putting the hole into each part of the choice. If you have a product, you have to choose between either putting the hole into the left part of the product or into the right part of the product, and you have to keep the other part of the product that's moving down to the left of the tree or moving down to the right of the tree. You put the hole in the left of the tree and you keep the right part of the tree. This is really Leibniz differential calculus. Now the way, and this is what the containers now do, is they actually explain this phenomenon in a systematic way, which we can use in this theory of experiments that I was talking about. If you write the container as a polynomial function written in this form with the exponential object for the function space, you can see that it gives you the form that you know from the differentiation of polynomials. And this goes all the way, and in particular, you now get actually Leibniz chain rule for the composition, which is really the hammer here. And this shows that there's a real systematic going on here. So I'm wondering now if I can use the differential structure of containers to think about automating and understanding algebraically a theory of experiments understood as a theory of holes in trees that can be filled in with different values, evaluated and experimentally explored. Thank you.
Thank you very much. I think in fact of our time considerations, we go to the coffee break and ask Jakob some questions over there. Thank you for your talk once again.
In dem Moment, wo es die Container anfingen und dann weiterging, von dem konnte man folgen. Also folgen, aber dann, das heißt nicht alles im Detail.
Ihr könnt den Bilder bei mir brauchen. Wenn ihr nicht an das richtig glaubt, sondern weil ich glaube, es ist das fünfte Weg, das ich
Dieses Jahr oder?
Ach so, sorry, wenn wir es nicht klauen. Klauen war das Wort.
I'm sorry. And I switch on. What? Super. Super.
Alles klar. Funktioniert. Also ich brauche den nicht, aber ich glaube, das ist vernünftig. Nee, ich mache weiter.
It's fun stuff.
Yeah, right. I saw it coming from afar. It's good stuff.
Yeah, it's good stuff.
But then you
you have the plus and the times on your containers.
Ja, du hast Summe, Produkt und dann hast du Komposition. Das ist der Kern. Aber der Hammer ist eigentlich Komposition.
Aber wo sind wir denn dann? Wo leben wir denn mit Summe, Produkt und Komposition?